Hi guys, and welcome to Chapter 14. Chapter 14 covers climate change. Specifically, it goes over to what climate is and what climate change is, some of how we study climate change, the effects and impacts of climate change, and some of the solutions or how we're going to have to deal with climate change as it gets worse and worse in the future. So for the first lecture, we'll be going over what climate is and what climate change is, and how climate change is exacerbated and caused. So basically, before we go into anything else, it's useful to do a recap of the difference between weather and climate. Remember that weather is short-term atmospheric conditions that occur over minutes, hours, days, or sometimes weeks if the storm is particularly long-lasting, versus climate. Climate are long-term patterns of atmospheric conditions over a given area over years, decades, or centuries. So climate is long-term, weather is short-term. And there are three major factors which affect climate, all of which we've gone over at some point in the past few previous lectures. So the sun, basically the sun is the source of almost all energy on the Earth's surface. The atmosphere, which is the protective layers of gases around the planet. We already talked about how the sun and the atmosphere and specifically convection dictate weather patterns as well as certain climate conditions around the planet. And then finally the oceans. We went over in chapter 12 how the oceans will store and transport energy via the heat capacity of the water as well as the circulating currents to distribute heat across the entire planet. So these are the three major factors that basically affect climate around the entire globe. Next, it'll probably be useful to introduce or define what climate change actually is. So climate change describes modifications in the Earth's climate, specifically temperature, precipitation, and storm frequency and storm intensity. This is not the same as global warming. Global warming focuses on only one aspect of climate change. It only looks at the average change in Earth's temperature. This is only one aspect and doesn't necessarily reflect some of the other damaging trends in climate, such as increasing precipitation, storm frequency and intensity, and different regime changes around the entire globe. So remember that climate change is different and more severe than global warming because global warming only focuses on one side of the issue and on one perspective, versus climate change looks at every impact associated with increasing greenhouse gases around the entire globe. So before we get into the mechanisms that result in climate change, it's really informative and really useful to go over the energy budget. Now, the energy budget is really complicated and pretty complex, so bear with me here as I try to break it down for you. First and foremost, you have the radiation that is incoming from the sun, basically solar radiation in the form of light and UV radiation that bombards the Earth's surface. Of the 100% of energy that hits the Earth from the sun, about 70% of it is actually absorbed. 23% of the solar radiation is absorbed in the atmosphere, and then 54% is absorbed on the Earth's hard surface. So remember, 70% of the solar radiation that the sun bombards the Earth with is absorbed, and about 30% of the radiation is actually just straight up reflected back out into space. Now, of the 70% of the sun's radiation that we retain, most is actually reflected straight out back into space in a different form. Remember we talked in chapter 13 that basically the Earth absorbs solar radiation in the form of UV radiation and light, and then re-emits that radiation in the form of thermal radiation or heat radiation back out into space. And most of this just leaves. So out of the 70% of the sun's radiation that we absorb, we re-emit about 86% of it. So out of that 70% that hits the Earth, only about 14% of it actually resides within the Earth at any given moment. The rest is just re-emitted back out into space. Now, the greenhouse effect refers to the phenomenon in which gases in the atmosphere actually reflect a portion of that thermal radiation being emitted out in space, trap it, and reflect it back down into the Earth. So it basically leaves the Earth a little bit warmer and a little more hospitable. Greenhouse gases are the gases specifically which reflect that thermal energy back down into the Earth and contribute to the greenhouse effect. Now, it should be noted that the greenhouse effect naturally is a very good thing. It has always existed, and it actually helps provide a more hospitable and warmer environment that can actually support life. Without the greenhouse effect, Earth would be far too cold to support any form of life, and so it keeps the Earth in a temperature range that is needed so that we can survive and that we can thrive. Unfortunately, humans have added too many greenhouse gases in too high quantities, which actually amplify and contribute to the greenhouse effect and make it much stronger than it otherwise would be naturally. This is actually now causing the climate to increase in temperature because it's trapping all of this energy, this excess energy that we don't need, and it is beginning to disrupt environmental processes and impact both humans and the environment at large. This is referred to as the anthropogenic intensification of the greenhouse effect. Anthropogenic just means human caused, intensification means enhanced, so you can think of it as the human enhanced greenhouse effect. And essentially this is the added greenhouse effect that we are contributing to by inserting greenhouse gases into the atmosphere in concentrations which would not occur naturally. So greenhouse gases, again, refer to those gases which reflect that thermal energy back to Earth and contribute to the greenhouse effect. And there are 5 major gases that do this, 4 of which are human amplified. 1 is simply natural. By far and away, carbon dioxide contributes the most to the anthropogenic greenhouse gas effect. However, nitrogen oxides or nitrous oxides, methane, and hydrochlorofluorocarbons also play a major role in the anthropogenic intensification of climate change and the greenhouse gas effect. Now, carbon dioxide is again the greenhouse gas which has contributed the majority of the warming in Earth's climate, and this is primarily produced through the burning of fossil fuels and the burning of forests, or the clearing of forests, which essentially releases stored carbon from the ground into the atmosphere. The majority of carbon emissions in the United States are caused by electricity generation of coal and transportation, so the burning of gasoline in our vehicles, our cars, so that we can move from place to place. The concentration of carbon dioxide now is at its highest point that it's been in 80,000 years. Again, this is not natural. We are 100% contributing increased emissions or increased concentrations of carbon dioxide into the atmosphere, which is contributing to the majority of the anthropogenic greenhouse gas effect. Next up is methane. Methane is a greenhouse gas that is actually stronger and more potent than carbon dioxide in terms of its warming potential. It's between 25 to 84 times as strong, whether you look at a quarter century or century-long time scale. So it's more potent than carbon dioxide, but it's not produced in as high a volume annually as carbon dioxide. Methane is primarily produced through the raising of livestock. Basically, cows and sheep and different ruminant animals will burp methane back into the atmosphere, and it is also produced as a byproduct of organic waste that is decaying or decomposing in different land dumps. And so again, even though methane is a stronger greenhouse gas than carbon dioxide, it is not emitted in nearly as high quantities, simply because we're not burning it or we're not releasing it as a result of fossil fuels, and so it is not contributing nearly as much to the greenhouse gas effect as carbon dioxide is. Next up are nitrous oxides. Nitrous oxides are far stronger than carbon dioxide. It is around 264 times as potent as carbon dioxide, and this is produced as a byproduct of feedlots, chemical manufacturing, and auto emissions. So this again is going to be far stronger than carbon dioxide, but because it is not produced in as high quantities, it doesn't contribute as much to the greenhouse gas effect. Finally, we have our hydrochlorofluorocarbons, and these are the most potent greenhouse gas. They are 10,000 plus times as strong as carbon dioxide, and they were originally produced as refrigerants and found in household products. However, since the Montreal Protocol, because these chemicals also contribute to the degradation of the ozone layer, these chemicals have drastically been reduced since 1988, and as a result, the concentrations have drastically decreased, and we don't really see them anymore. So mostly we focus on carbon dioxide and methane, the two which are released in higher volumes, which contribute to the majority of climate change seen on the planet. Now, the one greenhouse gas we haven't talked about yet is water vapor, and water vapor actually contributes the most to what is called the natural greenhouse effect, the greenhouse effect that occurs naturally without any human inputs. Now, the water vapor is not yet thought to contribute to the anthropogenic increase of the greenhouse gas effect, but it can be as conditions continue to change. And water vapor may actually soon exacerbate the greenhouse effect that we are causing through a positive feedback loop. So essentially what happens is as we add carbon dioxide into the atmosphere, we are essentially heating up the planet by increasing the amount of thermal radiation that is re-reflected from the atmosphere back down to the Earth. As the atmosphere begins to heat up, water vapor is evaporated at faster and faster rates. If water vapor continues to be emitted and held in the the atmosphere at higher and higher levels, this contributes more to the greenhouse gas effect and essentially warms the planet even faster. As the planet warms faster, more water vapor can be emitted and can be held in the atmosphere, which further exacerbates the climate change problem. So, while water vapor isn't yet a direct cause or direct problem for the anthropogenic intensification of the greenhouse gas effect, it may soon be an indirect amplifier of the anthropogenic greenhouse gas effect through the aforementioned positive feedback mechanism. So now that we've talked a little bit about the greenhouse effect and the greenhouse gases responsible for the anthropogenic intensification of the greenhouse effect, it's important to note just how fast these greenhouse gas concentrations are rising. They are rising exponentially in that J-shaped graph that we see so often when we talk about exponential growth. We are now seeing that in the form of concentrations of greenhouse gases, particularly after the Industrial Revolution, once we began heavily relying on fossil fuels as our primary energy source. Over the last 180 years, we have tremendously increased the ambient concentrations of CO2, methane, as well as nitrous oxide. And this will be a huge problem as we look farther and farther into the long-term effects of the greenhouse effect and what happens when the more severe implications of climate change begin to unfold. Now, next we're going to be talking a little bit about aerosols. Aerosols are microscopic particles which are suspended in the atmosphere. Now, they can have either a warming or a cooling effect on the environment. Black carbon, or basically soot, has a very strong global warming or climate change effect simply because it absorbs a tremendous amount of radiation and re-emits it as thermal radiation. So black carbon actually contributes to climate change and increasing the available heat energy in the atmosphere. However, black carbon aside, most aerosols actually cool the planet down. Most of the aerosols that are in the atmosphere reflect higher and higher concentrations of solar radiation back out into space. So sulfate aerosols, and particularly dust, do a very good job of actually cooling the planet. Now, for the final 4 slides of this lecture, we're going to be looking at some of the natural variations in climate, things such as the Milankovitch cycles, variations in solar output, ocean absorption, and ocean circulation. Now, a lot of climate deniers like to point to solar output and the Milankovitch cycles as responsible for the observed change in climate. However, we're going to go over specifically what the Milankovitch cycles are and the variations in solar output and why they honestly cannot be responsible for the observed change in climate, energy, and warming energy over the last 150 years since the Industrial Revolution. Now, the Milankovitch cycles refer to periodic changes in the Earth's rotation as well as the Earth's orbit around the Sun that can trigger substantial climate variation over time. However, these cycles operate on the scale of thousands and thousands of years, in some cases hundreds of thousands of years, and are very slow to enact. The first is called precession, or axis rotation, and this is the gradual change or wobble in the orientation of the Earth's axis with relationship to the Earth's tilt and its eccentricity. This is going to be the Milankovitch cycle over on the far right-hand side of your screen. Next is variation axis tilt. The tilt in the Earth's axis varies between 22.2 degrees and around 24.5 degrees. Now, the greater the tilt is, the more solar energy and solar output the poles receive, and because the poles have the majority of the ice around on the planet, they result in the greatest amount of reflectivity. So if there's a greater tilt, that means that there's more melting, and it means that there will be typically a hotter climate than if there is less of a tilt. Basically, eccentricity refers to orbit variation. The Earth encounters more variation in the energy that it receives from the Sun when the Earth's orbit is elongated than it does when the Earth's orbit is spherical. So spherical, it receives pretty much an even amount of energy as it cycles around the Sun. However, if the Earth's eccentricity or the Earth's orbit is elongated, that means twice a year the Earth is far closer to the Sun than it normally would be, and that means it receives more energy, resulting in a hotter temperature, ambient temperature, and hotter climates. Now again, it's really important to note that these variations in climate as a result of spatial relationship to the Sun as well as the tilt in the Earth's axis occur over tens to hundreds of thousands of years. The observed change in climate that we've seen so far has occurred over 150 years, so the scales just don't add up. If the climate was changing as a result of Milankovitch cycles, we would barely be able to detect it just because it would be unfolding so slowly. However, the fact that climate change and temperature variation variation has been so rapid in the last couple of decades is indicative that a much faster process is unfolding in order to facilitate this type of climate change. In addition, due to the orbit and the relationship that we have in the current Milankovitch cycles, the climate should actually be cooling instead of heating up. So if it were just Milankovitch cycles that were unfolding, that were driving the current observed climate change, the climate would actually be cooling down, not getting hotter and hotter as we're seeing currently. Now, variations in solar output is another source of variation in climate, or at least a assumed source in variation in climate. Remember that the sun supplies most of the Earth's energy, and it is responsible for driving most of the patterns in climate as well as the patterns in weather. Without the sun, our dominant energy source, the Earth would be dark and frozen and unable to support life. However, solar output varies on about a scale of 5 years, which it oscillates in high intensity to low intensity. However, and as a result of this oscillation, many climate deniers like to say that the sun's intensity is what's driving observed climate, not the increase in greenhouse gas emissions. However, this solar output varies by only about 0.05 watts per square meter per day, and in contrast, the total average solar output is around 1,366 watts per square meter per day. So the actual fraction at which the solar output varies is infinitesimal and could not possibly be the result or be the driver behind climate change. In addition, the solar output oscillation occurs on a period of about 10 years, and so it couldn't possibly be driving climate change over a scale of 150 years. So not only does it occur on too short of a time scale, it also is too small to really do any damage or have any effect on Earth's climate. Now, next we're going to talk a little bit about ocean absorption, not as a source for climate deniers, but more as a way of facilitating and mitigating the different sources of climate change as a result of greenhouse gas emissions specifically. Oceans actually absorb about half of all CO2 that is emitted. Now, again, this also contributes to ocean acidification, something we talked about in Chapter 12, but it also has a different implication when we look at climate change. Basically, by absorbing all of this CO2, the ocean's doing us a huge favor because it basically buffers the effects of CO2 in the atmosphere and reducing the amount of CO2 that is available to contribute to anthropogenic intensification of climate change. However, the oceans, as they are heating up, are absorbing less and less CO2. So soon, if the oceans get too hot, they will no longer be able to absorb any CO2, and the climate will warm even faster, about twice as fast as what we are currently seeing. So this is going to be a huge problem in the future, and is going to contribute to, it essentially is going to contribute to a positive feedback mechanism in which the climate will continue to get hotter and hotter simply because the oceans will no longer absorb any more CO2. Finally, natural variations in climate result from ocean circulation. Remember that the oceans will circulate and distribute energy around the entire globe in sort of a oceanic convection belt with warm surface currents as well as cold deep water currents. However, we also were talking briefly about how global warming or climate change is melting Greenland's ice sheet. As a result, that freshwater runoff is disrupting that convection belt and slowly slowing down that distribution of heat. If the current or if the ocean convection belt is stopped entirely, meaning that heat is no longer distributed up to Greenland, this could trigger a massive ice age simply because there's no longer any warm water that is being received in the polar latitudes of the globe. And again, under this scenario, if the convection belt stops, it can trigger a massive ice age, which also would be extremely problematic in that it could impact or kill a lot of people living in the northern or the high latitude regions of the globe, either in the northern or southern hemisphere, and it would also cause a lot of displacement issues. So this is also not a real scenario that we're going to be hoping for. However, that is the last slide for this lecture for going over climate. Next, we're going to be looking over studying the effects of climate change, how we are studying it, going back in time, looking at it presently, and projecting it into the future. And I look forward to talking to you guys again about that then.